Okay, picture this. You shine a light on a piece of metal. Now, you'd probably guess that the electrons inside would kind of warm up, absorb some energy, and maybe eventually wander off. But what if they were blasted out instantly? What if turning up the brightness of the light did almost nothing to their energy, but changing its color changed everything? Well, this one totally baffling experiment threw a giant wrench into everything we thought we knew about light, energy, and, well, reality itself. So let's trace this story. We're going to start with the total crisis that had physicists in the early 20th century scratching their heads. Then we'll get to Einstein's frankly revolutionary idea of the photon and break down the beautifully simple equation that explains it all. After that, we'll look at how we can control it and where this bizarre effect actually shows up in our daily lives, before we land on the profound, world-changing revelation it gave us about the universe. You see, for the longest time, everyone was pretty happy thinking of light as a continuous wave, kind of like ripples in the ocean. And that makes intuitive sense, right? A bigger, more intense ocean wave, a tsunami, is obviously going to deliver a whole lot more energy than a tiny ripple. So, a brighter, more intense beam of light should have a bigger punch. Simple. Except it didn't. And this is where things just went completely off the rails. The classic wave model made two very clear predictions. One, brighter light means more energetic electrons. Two, even a really dim light, if you just wait long enough, should let an electron soak up enough energy to escape. But what actually happened in the lab was just bizarre. The energy of the electrons had nothing to do with brightness. It depended only on the light's color, its frequency. And there was no waiting. The electrons were ejected immediately, or not at all. This left physicists with two huge, unexplained mysteries. First, that instantaneous emission. It was baffling. According to the wave theory, a dim light should have taken decades for an electron to absorb enough energy to get out. Yet, it happened in a flash. And then there was this weird rule, this threshold frequency. You could take the most powerful, intensely bright red spotlight you could imagine, shine it on certain metals, and nothing. Not a single electron would budge. But then, a faint, dim little violet light would come along and immediately start kicking them out. It made no sense. Let's be clear, this wasn't just a minor issue or a measurement error. The established laws of physics were fundamentally broken. The smooth, elegant wave theory that had explained so much for a century had slammed into a brick wall. And it wasn't just a small crack. It was a spectacular, total failure. Physics desperately needed a new idea. And that new idea arrived in 1905 from a young Albert Einstein. He proposed something so out there, so radical, that even the top physicists of the day were sure he was wrong. He said, what if light isn't a continuous wave at all? What if it's a stream of tiny, individual bullets of energy? He called these little energy packets light quanta. Today, we call them photons. In Einstein's picture, a beam of light is like a hailstorm of tiny energy particles. And here is the absolute key to the whole thing. The energy of a single photon isn't set by how bright the light is. It's determined only by its frequency, by its color. This insight boils down to one of the most important and honestly beautiful equations in physics. E equals h times f. The energy, E of one single photon, is just its frequency, f, multiplied by this incredibly tiny but universal number called Planck's constant, h. That's it. So higher frequency light, like blue or ultraviolet, is made of higher energy photons. And brighter light? Well, that just means you're firing more photons every second. So how does this photon model solve the whole mystery? Well, Einstein basically reframed the entire event as a simple, one-on-one, all-or-nothing transaction. It's not about a wave slowly warming things up. It's about one photon colliding with one electron and handing over all of its energy in a single, instantaneous shot. You can think of it like a simple energy budget for the electron. First, there's the income. The electron absorbs the full energy, hf, from a single photon. But then there's an expense. To escape the metal, it has to pay a fixed price, like an exit fee. Whatever energy is left over after paying that fee becomes its profit, the kinetic energy it uses to fly away from the surface. And that exit fee has a proper name. It's called the work function, and we represent it with the Greek letter phi. It's literally the price of freedom. It's the bare minimum energy an electron needs to pay to break free from that specific metal, and every material has its own unique work function.
And all of this comes together in one incredibly clean and powerful equation. The electron's maximum kinetic energy, Kmax, is simply the photon's energy, hf, times minus the work function, phi. It's really just a statement about the conservation of energy for this tiny quantum event. Income minus expenses equals profit.
And with this one equation, both of those big mysteries are solved, just like that. Why is there a threshold frequency? Simple. If the incoming photon's energy, hf, is less than the work function, the electron just doesn't have enough to pay the exit fee. The deal's off. Nothing happens. And why does the electron's energy depend on color? Well, the equation shows it plain as day. Kmax goes up in a perfectly straight line as you increase the frequency, f. Brightness isn't even in the equation. So this really clarifies things. It means we have two completely independent knobs we can turn in this experiment: the frequency of the light, its color, and the intensity of the light, its brightness. And Einstein's model makes it crystal clear that they do two totally different jobs.
Okay, this table nails it. Let's break it down. When you change the frequency, the color, you are changing the energy of each individual photon. That's what determines the kick each electron gets. But when you change the intensity, the brightness, all you're doing is changing the number of photons you're sending per second. It's like switching from a single rifle to a machine gun. You're firing more bullets, but each individual bullet still has the exact same punch. So brightness gives you more electrons, but color gives you more energetic electrons.
So you might be asking, how do we actually measure the kinetic energy of these flying electrons? It's pretty clever, actually. We can apply an opposing electric field that creates a voltage that pushes back on them. We call it the stopping potential. We just crank up that voltage until we stop even the most energetic electrons in their tracks, and that voltage tells us exactly what their maximum kinetic energy was. And when scientists went into the lab and did this, what they found was just perfect. If you plot the maximum kinetic energy you measure on the y-axis against the frequency of the light you used on the x-axis, you get a perfect straight line, exactly as Einstein's equation predicted. This graph was the smoking gun. It was the undeniable proof that his crazy idea about photons was right all along.
Now, this isn't just some dusty, 100-year-old physics puzzle. This principle is one of the most practical and important discoveries in all of science, and it powers technology that we use every single day.
The light sensor in your smartphone camera? That's the photoelectric effect. The automatic doors that open at the grocery store? Yep, same idea. Solar panels on a roof converting sunlight into electricity? That is literally the photoelectric effect in action, liberating electrons to create a current. It's used in incredibly sensitive devices that can detect a single photon from a distant galaxy, and it even helps us analyze the precise chemical makeup of materials. It even has to be accounted for on spacecraft, because sunlight is constantly knocking electrons off their hulls out in space. So what started as a little experimental puzzle ended up triggering a complete and total revolution in how we see reality. This one experiment forced physics to abandon this centuries-old picture of a smooth, continuous world. In fact, the photoelectric effect was the very first piece of undeniable, concrete evidence for the quantum nature of light. It was the first domino to fall in a chain reaction that would eventually lead to the entire incredible field of quantum mechanics. So, what's the deep insight here? What's the fundamental takeaway from all of this? It's that energy is not a smooth, flowing river. It's more like a rain of individual droplets. At its most fundamental level, energy is transferred in discrete, all-or-nothing packets. Nature, it turns out, is granular.
And that has to leave you with a pretty profound question. The photoelectric effect showed us that light and energy are quantized. They come in little chunks. So what else is? What other parts of our universe that seem so smooth and continuous to us are actually built out of tiny, discrete, fundamental units?